Okay, hello. So there's going to be a recorded lecture. I've decided to do it on a side topic, so it doesn't quite follow from what was done in lecture 17. This will be lecture 18, but it's a somewhat self-contained topic, so we should be able to do something that makes sense and continue from where we left in lecture 17 when we do lecture 19. Okay, let's get started. All right, let's get to our screen. And this lecture is going to be on numerical solution of these, but with focus on a particular type problems, that is boundary value problems. And you'll find this I'm listed as BVP. Now, let's see what we mean by this. We're going to have some domain, and let me change maybe the color here on my pen. X0, there's going to be X. I'm going to use an N. We're going to discretize this anyway. And I'm going to have boundary conditions that are assigned in both points. Okay, now that I should immediately tell you something about what is going on here. So let's see how this goes. You have at least two boundary conditions, because I'm saying I'm going to assign boundary conditions in both ends of this interval. And if I have at least two boundary conditions, my equation needs to be at least a second order differential equation. And in fact, equations of this type are typically equilibrium problems. Now, let's see what we can do with this. We've looked at initial value problems where we start from one end of the 1 point, x equals 0, t equals 0, or any number for that matter. And we march our solution, and we call these march methods. We march our solution from one end of this interval to wherever we need to go. And if we have a second order equation, formally I can say, well, let me assign both boundary conditions in the initial point and march from there. Now, again, we can't quite do that because we only have one boundary condition in the initial point. Therefore, we need to come up with something different. And there are actually many methods, but I would say there are two general categories. Numerical families of methods to solve boundary value problems. And those are shooting type methods and equilibrium methods. Let's start with the first ones. Shooting type methods. Okay, see, oops, trying to copy here. So the general idea is to take a guess for the value of the boundary conditions on one side of the interval that are not known, and integrate to the opposite side and hope for the best that you find on the opposite side the value of the function or the value of its derivative match what the assigned boundary conditions are. That is typically not the case. So you need to come up with something more clever. Okay, so what do we do? Let's consider an example. Let me share my screen again. Let's say we want to solve this equation. Second derivative of y with respect to x squared is equal to some function of x that is a sine. Y of 0 is equal to y0. Y of some other value, let me call it L, is equal to y sub L. What I'm going to do is try y of 0 equal to y0, y prime of 0 equal to some value, let me call it a. Now, the standard methods that we started talking about for integrating initial value problems typically deal with first order equations. And this is a second order equation. But I have two initial conditions in the same point, so I can treat this with a matching method, as long as my matching method is capable of solving a second order equation instead of a first order equation. If you remember, this is something we've already encountered. I can define function z of x. Sorry, that my pen slipped. That looks horrible. Let me write that again for the sake of beauty. Okay, I can define a function z of x equal to y prime of x. This is a definition. Then I can follow the system of equation. So that also means that z prime of x is equal to y double prime of x. So I can solve the equation y prime of x equals z, and z prime of x equal f of x, where y of 0 is given, z of 0 is given in the sense that I'm guessing it, right? Didn't say this. I do not remember actually if I did say this explicitly, but this was some type equation. And in fact, instead of just a function of x, I could pretty much have anything there. Function of x and y, it doesn't need to be linear. We'll come back to that. Okay, so what do I do next? I'm going to solve, and I'm going to calculate y, oh, sorry, lowercase y of L. And guaranteed that if I make an arbitrary guess, I'm not going to find the correct value. But now I can see this as y of L is equal to some function of my initial guess A. So the value that I get in on the far side of my boundary, where I wasn't directly able to apply the boundary condition, is going to depend on what I guessed for the boundary condition. And what I can define is an auxiliary function for beauty, another arrow there. And I'm going to define a function h of a, oh, that's an a, equal to g of a minus y sub l. And you see what I've done. I defined a function that needs to be 0 if my guess for the boundary condition for the derivative of y on the left-hand side is correct. So I reduce my problem to the following. Oops, h of a equals 0. And we're in good shape here. We know how to do this. This is a defining problem. So, okay, in practice, we started with boundary value problem, and we turned it into a combination of initial value problem and a root finding problem. So conceptually, this is all there is into shooting methods. There are some tricks and invariants and alternatives. Just going to hand wave my hands a little bit. I'll just mention that example because I showed it in class the other day. Let's see. Find yeah. Let's say I'm working on a problem of this type. Where my solution does something like this. So if I look at the plot a little bit lower, that my solution gets pretty flat here. So that may cause some issues. May have the value that solution gets to is very sensitive to the boundary conditions that I'm guessing. In fact, honestly, I'm actually doing this using a shooting method, and it kind of works okay. But one other approach that you can do is, since the equation you're solving is not homogeneous, you don't have any arbitrary constants, then you can start integrating from both sides with a shooting method from both sides and find the derivatives that will make the solutions match in the middle. Is this better? No. But for some special cases, you may find that is an option that works better. Okay, now there is, of course, always more into this type of problems. I've used the easiest, easiest to approximate condition, that is what's called the Dirichlet boundary condition. Maybe let me share my screen again and actually type it. I'm sure you're familiar with this, but let's see, where's my screen? Where I'm assigning the value of the function. And the Neumann bound, for the Neumann boundary condition, I'm assigning the value of the derivative. I'm putting first into brackets because it should be obvious it's the first, but never know. So what happens if I have a Neumann type boundary condition instead of a Dirichlet type boundary condition? Not much. I make this work. I make this go in the same exact way, except that what I'm given in my notation here is the value of z at the far boundary. And if I start with that's the function I need to set to 0. Z at the far boundary minus the assigned value needs to be equal to 0. Or I may have derivatives assigned to both sides. And then what I need to guess is the value of the function. Same thing. You may have some more complicated boundary conditions. Let's go for the neck, but where you have a combination of the value of the function and the value of the derivative. So what you do in that case, you're not given either. So let's say that's a point where you have the boundary condition on the side you start integrating from. You know that that's not how you spell value. It's crazy. You have something like this. C0 times y equals 0 plus C1 times y prime equals 0 is equal to some number. Could be 0, could be some other number. Well, I want to start integrating from here. I assign a value for one of them, for instance, the value of the function. This relation immediately gives me the value of the derivative. Now I got the initial conditions, and I can start integrating from here and proceed exactly like I did before. Okay. Now there is still a little bit more that we can do. Of course, you could do the opposite, assign y prime. It doesn't make a difference. This is all nice and great. So I feel that we got at least conceptually a good method for solving this problem. You may notice that the method that usually works well, the Newton method, can't be used in this case because I don't have analytic expression for the derivative. So what do you do? And this is a pretty standard way to proceed. And do a numerical approximation. Call my function here h. The reason is that, as we've seen many times, the Newton method is pretty often a method that converges pretty quickly. So what do you do in that case? You're going to do the following. Say how much do I need to get into detail? Probably not terribly much, but let's just be extremely explicit. So what you do, I'm going to assign y prime for 0. I'm again thinking of the problem we started from. This is what I'm solving. And these are the boundary conditions. And you can easily figure out what to do in the case the boundary condition, the one or the side or the other is not a simple Dirichlet boundary condition. Okay. So oops, not 0. This A. I'm going to calculate h of A. You remember what that was. And here I need to use a symbol. Yeah, I do it this way. I'm going to assume sign value instead of the value started from a value that's a little different from that original value. Much less than whatever it needs to be. So it could be a could be something else. I have to make it small in terms that are meaningful for my problem. Okay, and then you see what you have. Oops. So if I do that, I can estimate. No. But I don't remember what the fractions here. Let's see. No. Okay. Well, I estimated this derivative. It would be so nice if this thing used LaTeX. And then I proceed. Aha, it actually worked. Mm. Oh, no, yeah. Okay. Calculate next. Okay, that's what I do. I have the value of the function, I have the value of the derivative. Then I can use the Newton method to try to find the zero. So that's the the natural logical process that you use for this type of problem. Now, this is all looking, well, I hope it's all looking good and clear, but that's still not the end of the story. What happens if the equation you're trying to solve is not a second order equation? And there are problems in physics. I'm not going to give you any specific example. You can find problems where the equation is higher order than the second order, or you could have a system of equations. And that's again the boundary layer problem that I showed you has two equations, sort of a density and a velocity, and you need to solve both at the same time. So in that case, you can sort of do the same thing. You can still write this as a system of equations. Let's say we have two couple second order equations. So you can rewrite them as a system of four first order equations. And proceed as before, except that now I'm trying to, so let's say I have this type of problem. I have second derivative of y with respect to x squared is equal to f of x, and second derivative, see, I've already used all the letters in the alphabet. So I would call this big Y, but I'm going to make a mess. Okay, let's use W. W is a good letter. And instead of don't call this F1 and F2, I could have used Y1 and Y2. Didn't think of that. So I'm assigning the same boundary conditions as before. For the first equation, I'm assigning W of 0 is some value W0, W of L is some value W sub L. Then I'm going to do, as I promised, the same thing. I'm going to try some values for the derivative. See y prime of 0 equal a and w prime of 0 equal b. And then I can integrate from 0 to L as before. And what I'm trying to make equal to 0 is some function h of a and b, which is equal to y of L minus yl, and maybe a little more clear here. Let's say this one of L, having assumed that A is a derivative, minus YL, and this function is going to be W of L with the assumed derivative B minus WL. So H is a vector function. Okay, so what I have to solve at this point is zero root finding problem with two parameters and two equations. And you hopefully remember how to do that. But if not, normally what you do is use the Newton method. with derivatives of h, big H, with respect to the two parameters, the two guesses. And since I don't have an explicit analytic expression for h and for its derivative, I do the same thing. What you do is pick an A and a B, and then redo the calculation. So maybe write it explicitly. I'm just going to write it by hand. It's going to be faster. One, I'm going to assume y prime 0 equal A, y prime, sorry, w prime and this gives me h of A and B. My next attempt, I'm going to do y prime 0 equal to A plus delta A, W prime of 0 still going to be equal to B, and that gives me H of A plus delta A, B. My third attempt is going to be Y prime of 0 equal to A, W prime of 0 equal to B plus delta B, and I'm going to obtain H of A and B plus delta B. Okay, so and these are enough to get the partial derivatives of H. So these two can use to get the derivatives. Oops, the straight line. Thank you. Partial derivative of H with respect to A, and this is going to be the partial derivative of H with respect to B. There you go. And it will hopefully sync in a moment, and then you're pretty much done. Okay, so this method you can use if you have a higher order equation. You sort of do the same thing, and there may be a number of combinations. In most cases, what you're going to find is second order equations, and if they're coupled, this is how you proceed. If you have a higher order equation, you sort of treat it in the same way. But you may have a different number. I can't think of any physics problem that will look that way, but in principle, you could have a different number of boundary conditions in one side with respect to the other side. And then, needless to say, you start integrating from the side where you have more boundary conditions. So you have fewer parameters to guess. Okay, mostly spend too terribly much time on this because I would like us to also briefly look at the other option, which is here, equilibrium methods. So let's consider let's consider those next. Why are they called equilibrium methods? Not entirely sure, but though they are. So let me make perhaps this a little bit more formal here. Let me write the system as sorry, not the system, the equation as d to y dx squared plus p, which in principle can be function of x and y, dy dx plus q, again function of x and y in general, times y is equal to some f. I use lowercase f. Let's make it uppercase here since I have the uppercase coefficients. And let's again assume, sorry, we call them x1 and x2. I don't know if that's going to confuse the notation. Let's use 0. Now, clearly, the way this equation is written, it's in principle nonlinear. So this is the general expression. But for this type of method, let's focus on the linear case where we have essentially the same expression, but I'm going to assume that it's not only linear, it's a constant coefficients. It doesn't need to be, but I want it to be linear. And I'll be more explicit on why. I mean, we'll see in a moment why that is necessary. Actually, there are various ways to solve this type of problem, but let's assume that we do what we've been doing so far. I'm going to use finite differences to approximate my my problem. So I have first and second derivatives. I'm going to use the expressions we already seen in class. Second derivative of y with respect to x squared, going to approximate with, well, let's say a point, some point x sub I is going to be equal x I plus 1 minus 2 x I plus x I minus 1 divided by delta x squared. And for the first derivative, there are, of course, many methods, many approximations. The one for the second derivative I wrote there is kind of the standard one because it's the simplest one you can write in second order accurate. It's not equal sign, it's approximately equal. So for this one, oops, sorry about that. It's not x, it's y. So here I'm going to write y I plus 1 minus y minus 1 and here I'm going to have 2 delta x. See that's a little smaller than it should be. So let's see, it should be. This is probably going to backfire terribly. Let me try. That I did. All right. Sorry about that. Let me just rewrite it. Okay, yi plus 1 minus yi minus 1 divided by delta by 2 delta x. Okay, I got this part. Now, let me say, also, I'm going to allow p to be p of x, but not of y, and q to be q of x, but not of y. So this still makes the equation linear. Then what I'm going to have is looking at the equation that I'm trying to solve, this equation here. I'm going to have second derivative. I'm going to just copy y plus 1 minus 2 y sub I plus I y I minus 1 divided by delta x squared plus p sub I, which is p calculated point x I y I plus 1 minus y I minus 2 delta x plus q sub I y sub I is equal to f sub I, where all symbols should be pretty straightforward. Okay, now what do we see here? I have I plus 1 appear here and here. I have I minus 1 appear here and here. And, well, y sub I only appears in one point. So what I can do is collect the coefficients of each one of these. Let me start from I minus 1. So y I minus 1 is going to multiply 1 over delta x squared, and then pi minus p sub I over 2 delta x. Y sub I is multiplying minus 2 over delta x squared. No, sorry. Let's this up. In general, I may have a non-term, so I'm also going to have the QPs. So that would be with the plus sign plus Q sub I. Then I have plus 1, so y I plus 1 is going to have the same coefficients of the I minus 1, except that P is not P. No, yes, sorry, the approximation I use is PI. P over 2 delta x. Okay, should have everything, and this is equal to f sub I, and then I multiply over by delta x squared, just for convenience, and I find 1 minus p sub I. P sub I over 2 delta x, 1 minus 1, plus q sub I. Nope, it's not how I want to write it for beauty reasons. 2 plus qi times delta x squared, y sub I, and then I have the same coefficient here, pi sub 2 divided by 2 delta x times yi plus 1. This is equal to fi delta x squared. Okay, so this is the equation. Let me square it. In point I. And I'm going to apply this equation in all points from 2 to n minus 1, where n is the number of points I'm using. And hopefully you can see why, but if not, let's look at it together. So here I have, I was using 0, right? Yeah. X equals 0, x equal L, this point 1. Sometimes you'll find that as point 0, it doesn't matter, you just number the points any way you want. This point 2, this point n minus 1, and so on. So I know the values in the points 1 and n. So I'm not going to write this equation. The equation is half squared in those points. Because again, I already know what the value is. So I can do, conceptually, I can do this in 2 different ways. You can write a system of equations that looks like this. Let me call the reduce C. So I'm going to call, let me use this definition. I'm going to call this S sub I, and minus 2 plus qi delta x square. I'm going to call d sub I. Okay, then the equations I'm writing look like this. Y1 is equal to Y0 for the second point. I'm going to have S2 Y1 plus D2 Y2 plus S2 Y3 is equal to F2 delta x squared, and then it goes this way as 3 times y2 plus d3 times y3 plus s3 4 is equal to f3 delta x squared, and this keeps going until I get to s and my sorry, using uppercase and minus 1 yn minus 1 plus d n minus 1 times y n minus 1 plus s n minus 1 times y n plus 1. No, can't do that. And this was n minus 2. To be careful with my indices. So n minus 2, n minus 1, and then n is equal to f n minus 1 delta x squared. And the last equation is yn is equal to y sub l. I have n equations in unknowns, with the first and last equation being trivial, but they're still equations. So then I can write this as a system of linear equations. Not that these are, of course, linear. So that's option 1. There is another thing that you can do. Let's see if I can make this work. Just thinking. I'm not going to rewrite the whole thing. Draw. Yes. Okay, let's select. Okay, let's give myself a little bit more space. And the other thing that I can do is say, well, I know y1. y1 is equal to y0. So why not I just replace y1 in there? Then if I do that, I'm not going to write this equation, and I'm going to do the same thing for yn. And then what I'm going to do is take this and bring it to the right hand side. And the same thing here for the last equation, except that I'm going to remove the last term instead of the first one. So that's going to be minus s n minus 1 y is value. So how much time we have left? Oh, okay, time flies when you're having fun. In this case, I'm going to have n minus 2 equations in n minus 2 unknowns, but I'm going to get the same result. So in the first case, my matrix is going to look like this. I'm going to have an element here, we call it D1, which is 1. Then I'm going to have D2, S1, S1, D3, S, no, sorry, I got my indexes. So those are two. I'm going to do the whole thing. So this is S2, S2, is D3, S3, S3, Dn minus 1, Sn minus 1, Sn minus 1, and then Dn times a vector y, which is y1, yn, equal to f1, fn, where no, sorry, I should use a different symbol. Call this G. G1 is equal to y sub 0, and G2 CG is equal to f2 delta x, f2 delta x squared. And in the other case, I'm basically taking only this part of the matrix may go too far. Only this part of the matrix. And I'm moving the Sn minus 1, those two pieces to the right hand side. Okay, let's see. I think that's about it. But what do you do if your boundary conditions are not Dirichlet type boundary conditions? Then you you have various options. You can basically what you do is write an approximation for the derivative at the first and last point, and you can do it in any of the ways that we've found. So you can use a one-sided derivative and use only 2 points, or you can use more than 2 points. You can use any expression as complicated as you like for the derivative. Um, one so the way we wrote it, um, the system gives us a tridiagonal matrix. And if you remember, we didn't get into much detail, but there are very fast methods for solving a linear system where the matrix is a tridiagonal. So we're solving A times Y equal some vector G. So this is a pretty efficient way to do it. Does this work better than the shooting method? There are different methods. In general, it might work better. Which one is preferable depends on number of circumstances. One is type of choice, type of circumstance is going to force your hand. Or at least not trivially, not as easily as we've done here. And the reason is that that will not give me a linear system. That's pretty much all there is to it. So on the other hand, the shooting method makes no assumption of what I dare call lowercase f looks like. Here I said it's just going to be some f of x, but this could be f of x and y and could be highly nonlinear. It doesn't matter. I'm going to integrate my system to integrate my equation using a marching method where on the right hand side I'm going to have an equation that can be as complicated as it can be, but as long as I'm using a method that allows me to calculate the value of the right hand side based on information as is already known, such as a forward Euler method or some of the other methods that we'll see later in the course. I don't care that the system is nonlinear. And once again, to refer to that boundary layer problem that I showed you in class, that I'm actually working on for a research project, that's highly nonlinear. And that I'm solving with the shooting method. Okay, so that's I think pretty much all there is to it. For the equilibrium method, if you have coupled equations, as long as they're linear, you sort of proceed in the same way. So you have this matrix for, let me go back down, this matrix for y, and you're going to have another matrix where the unknown is, we call it w in the example, And the one thing you will have to decide there is how to advance. So you can make a vector of unknowns that is all the y's starting from point 1 to point n, and then all the w's starting from point 1 to point n, or you can have as unknowns y1 and then w1, then y2 and w2, and so on. And the choice, you're going to get the same result. What's the best choice depends on what your equation looks like. If the equations are coupled, typically you want to try to keep the matrix so that non-zero terms on in your matrix A are clustered together. So you're more likely going to be better off having the the unknowns in the same point, all the unknowns in the same point, and then move to the next point, have all the unknowns in the same point, and so on and so forth. Okay, I think according to my watch that I keep looking at, there would be another few minutes, but I don't want to drag it too long. Hopefully this gives you an idea of how to treat boundary value problems. The one more thing that you can possibly encounter is higher order derivatives. And if you want to solve that as an equilibrium problem, you do it again in the same identical way, but you'll have to insert the numerical approximations, the finite difference approximation of whatever derivative you have here. So if you have a third derivative, it's going to be whatever the expression is that you choose, and there you may have to fuss a little bit with what approximation you choose at the close to the boundary, where sort of don't have as many points as you like in both directions. And the last, I promise, thing is so that for higher order derivatives, what if for any reason you need delta x not to be a constant? That's okay. It doesn't need to be. What's going to happen is that your coefficient will look a little more messy, and you'll have to calculate the exact coefficient in each point. So let's say, for instance, q is 0. Then for this equation, you just have -2 everywhere. If delta x is not the same everywhere, you have -2 that multiplies some combination of delta x and point I plus 1, I minus 1, and I. And so on the diagonal, you will not have always the same value. Oh, and by the way, if you make delta x small, you're guaranteed that you have a big coefficient here. That's -2 is big in absolute value, regardless of what q sub I is. And that's, as we've seen for numerical solution of linear systems, that's usually a good thing. You don't want zeros on there. So something to keep in mind when you pick your discretization. All right, I'm going to close it here, and thank you for your attention, and I will see you in class.